A single drop of water falls into a still pond. The surface trembles, then fractures into widening ripples, each one flowing outward into its own pattern, never to be repeated. From that single drop emerges not one outcome, but many, each spreading, colliding, and merging with the others. It is a picture of possibility made visible, a metaphor for reality itself. For what if the universe behaves in the same way? What if every choice, every flicker of chance, divides existence into countless parallel realities? One where a step was taken, another where it was not. One where a word was spoken, another where silence lingered. What if the cosmos itself insists on every outcome being real, not as imagination, but as truth? Human perception longs for stability. We feel life as a single unfolding thread, where moments follow one another in orderly succession. Yet the quantum realm resists this simplicity. In its language, particles refuse to be bound by one fate. An electron may spin both up and down. A photon may travel both paths at once, until forced to reveal a choice. To scientists, this is superposition. To philosophers, it is the possibility that reality itself does not collapse but branches. And so the stakes deepen. Every decision, the smallest breath, the grandest event, may not merely be experienced or lost, but eternally preserved in some parallel strand of existence. If reality splits with every choice we make, then how many versions of us are already out there, living the lives we did not choose? If this journey into the mysteries of time and existence moves you, gently tap like, subscribe for more cinematic explorations, and share where in the world you are listening from, so we can journey together across space and across realities. At the dawn of the 20th century, the world of physics stood upon foundations thought to be unshakable. Newton's mechanics described the motions of planets and falling apples alike with uncanny precision. Maxwell's equations had revealed light itself to be a wave moving through the electromagnetic field. The universe, it seemed, was a clockwork mechanism, orderly, continuous, and predictable, yet hidden within the glow of heated metals and the delicate structure of atoms. A storm of uncertainty was preparing to rewrite reality. In 1900, Max Planck, reluctant and almost unwilling, introduced a strange mathematical fix to explain the spectrum of black-body radiation, the light emitted by objects as they warm. He proposed that energy did not flow continuously, like water from a tap, but was released in discrete packets, quanta. He called this a desperate act, a tool to make the equations work. Yet this simple step would break open the boundaries of classical thought. The seed of quantum theory had been planted, though its meaning remained obscure, even to Planck himself. Soon, experiments revealed behaviors no smooth, deterministic picture could contain. Light could act as both particle and wave. Electrons refused to move in tidy orbits, instead forming clouds of probability. Niels Bohr, in Copenhagen, sought to tame the chaos. His interpretation was pragmatic. A particle does not possess definite properties until it is observed. Between measurement, it exists only as probability, a ghost of possibilities hovering in superposition. For Bohr, physics did not describe reality as it is, but only what we can say about it once we look. The philosophical shock was profound. What does it mean for existence to hinge upon observation? If particles wait to be measured before they become real, then what lies beneath the surface of perception? Erwin Schrödinger, troubled by this vagueness, sharpened the paradox into a thought experiment. A cat, sealed within a box, connected to a device triggered by radioactive decay, would, according to the equations, be both alive and dead until observed. It was meant as a critique, an absurdity, pointing to the incompleteness of the Copenhagen view. Yet it became one of the most enduring symbols of quantum strangeness. Superposition carried into the macroscopic world. Decades passed, and quantum mechanics flourished, not through philosophical clarity, but through astonishing predictive power. It described semiconductors, lasers, the binding of molecules, the glow of stars. Engineers wielded its mathematics with confidence, even as philosophers wrestled with its implications. At the heart of the theory lay an uncomfortable rift, the measurement problem. Why does observation seem to collapse a cloud of probabilities into one concrete outcome? What counts as an observer? And why should consciousness or any act of measurement carry such cosmological weight? In 1957, within the quiet halls of Princeton University, a young graduate student named Hugh Everett offered an audacious answer. In his doctoral thesis, Relative State Formulation of Quantum Mechanics, Everett proposed that the wave function never collapses. The equations, he argued, describe reality fully and without need of reduction. Every possible outcome of a quantum event continues to exist, not as discarded alternatives, but as branches of reality itself. When a measurement occurs, the universe does not choose one fate. It divides seamlessly into many. In Everett's vision, the cat is both alive and dead, not in one universe, but in two. The experimenter observing one version of the cat finds herself within a corresponding version of reality, while another version of her watches the opposite outcome. With every quantum event, with every flicker of chance, the cosmos branches. The many worlds interpretation was born, but such a radical view met resistance. To a community already fatigued by the interpretive battles of quantum theory, Everett's multiverse sounded extravagant. Why multiply realities beyond necessity? Where was the evidence? Niels Bohr and his colleagues dismissed it with a wave of the hand, preferring the Copenhagen pragmatism that had already carried decades of success. Some labeled it philosophy rather than physics, untestable speculation dressed in equations. For years, Everett's idea lingered at the margins, noted by a few, but largely ignored. Yet the seed had been planted. Beneath its strangeness lay a ruthless consistency. Unlike Copenhagen, Everett's formulation required no special role for observers, no mysterious collapse of the wave function, no privileged line between quantum and classical. It was an unflinching reading of the mathematics, however unsettling the implications. If true, then reality is not singular, but plural, not flowing along one thread, but branching endlessly into a fractal of possibilities. At first, it seemed impossible to grasp. How could there be countless versions of the same person, living lives defined by choices they did not feel they made? How could an ordinary coin toss fracture the universe into dual realities? One where the coin landed heads, another where it landed tails. The mind recoiled, yet the equations stood firm. Everett's multiverse required no new physics, no alteration of quantum law. It asked only that reality be taken at face value. Over time, a quiet circle of physicists began to take the idea seriously. Bryce DeWitt, decades later, would champion it under the name Many Worlds, arguing that it was not fantasy, but the natural consequence of quantum mechanics left uncollapsed. The Copenhagen school had offered pragmatism. Everett had offered ontology. Thus began the slow unfolding of a question that still haunts physics today. Does reality truly split with every quantum choice? If Everett is right, then the world we know is only one strand in an immeasurable web. Our perception of a single unfolding life is not the whole story, but the narrowing of attention upon a single path, while countless others stretch away unseen. What was once ridiculed as extravagant speculation now lingers as one of the most profound possibilities science has ever dared to consider. The discovery was not an experimental flash, nor the stroke of a telescope's mirror. It was an idea, an interpretation that challenged the very meaning of reality. And from that seed, the question would only grow. If the universe divides, how many of us are already out there, living the lives we did not choose? When Hugh Everett presented his idea, he did not simply offer another interpretation of quantum mechanics. He proposed something far more disruptive, a vision of reality that fractured the very ground beneath human intuition. At its heart was a bold claim: there is no single reality. Instead, every quantum event, no matter how small, births a branching of worlds. To physicists trained in classical thought, the claim was paradigm-breaking. For centuries, the laws of nature had been regarded as the guardians of order. A planet moved in a calculable orbit. A pendulum swung in predictable rhythm. A stone fell with acceleration that could be measured and repeated. The universe was one, singular, continuous. Everett's proposal shattered this unity. Each measurement, he argued, does not collapse probabilities into one outcome. It preserves them all, each within its own universe. The shock was not in the mathematics. Everett used the same equations of quantum theory that his peers did. The shock was in the interpretation. If he was correct, then every spin of an electron, every photon passing through a slit, every decay of an atom generates a fork in reality. At each fork, the universe does not choose, it multiplies. To contemplate this is to confront infinity, not as abstraction, but as the architecture of existence. Human intuition, so accustomed to singularity, recoiled. We believe ourselves unique, observers bound to one continuous thread of life. Yet Everett's worlds deny this uniqueness. With every choice, countless versions of us bloom into being. One turning left, another turning right, one speaking a word, another remaining silent. We exist not as singular beings, but as constellations of selves scattered across parallel realities. The idea is not just strange, it is unsettling, even terrifying. It also defied the classical worldview. Newton's mechanics, and even Einstein's relativity, upheld a universe of determinism. From present conditions, the future unfolded with inevitability. Everett's many worlds introduced a universe not of one future, but of infinite multiplicities. Determinism was replaced not with chaos, but with proliferation. Every possible outcome was determined, but determined in different worlds. To ask which was real became meaningless. They all were. This confrontation between determinism and multiplicity echoed the unease Einstein himself had felt with quantum theory. The randomness of measurement offended his sensibilities. God does not play dice, he famously remarked, objecting to the idea that nature at its core was governed by chance. For Einstein, quantum mechanics was incomplete, a provisional framework awaiting hidden variables that would restore order to the universe. Everett, by contrast, did not reject the dice. He insisted they never stopped rolling, not in one game, but in countless. Later, Stephen Hawking would reflect on these questions through the lens of cosmology. In quantum cosmology, where the entire universe is treated as a quantum system, the uncertainty of beginnings became fertile ground for speculation. Hawking suggested that universes themselves could bud from quantum fluctuations, emerging from uncertainty like foam upon the sea. If this is true, then Everett's branching may not merely describe particles or atoms, but entire cosmoses. The multiverse becomes not metaphor, but possibility, an endless bloom of worlds, each carrying its own version of events. Why was it so hard to believe? Because Everett's claim multiplied existence to an incomprehensible degree. It required not just one universe, but infinity upon infinity, each branching at every instant, each containing uncountable versions of reality, and yet it offered no observational evidence. Telescopes could not peer into these parallel worlds. Detectors could not catch their presence. The mathematics permitted them, but the instruments remained silent. To many, this was extravagance. To believe Everett required a leap into a cosmos where reality itself is excess without end. The shock of many worlds was not that it contradicted the equations of physics, but that it contradicted the very instincts of the human mind. It left us suspended in a question that still hangs unresolved. If reality branches endlessly, then who are we in the face of infinity? The strangeness of Everett's vision could not stand apart from experiment. Quantum mechanics was never only a philosophy. It was a science born from the laboratory, from the flicker of detectors and the patterns on screens. To trace the truth of many worlds, one must return to the experiments that first revealed the quantum realm in its paradoxical light. The double-slit experiment remains the fountainhead of this mystery. When a beam of light or even a stream of single electrons is passed through two narrow openings, the particles leave behind not two bands, but a delicate interference pattern, as though each particle had passed through both slits simultaneously, interfering with itself. If detectors are placed to observe which slit the particle passes through, the pattern collapses into two simple bands, as if the particle, under the gaze of measurement, chooses one path. Without observation, it takes them all. With observation, reality crystallizes into one. This strange duality, particle and wave, Multiplicity and singularity has stood as one of the most repeated confirmations of quantum mechanics. And at its heart lies the question Everett dared to answer. Perhaps the particle does not collapse into one outcome. Perhaps both outcomes happen in separate branches of reality. Modern quantum optics has sharpened the paradox into even more startling forms. The delayed choice quantum eraser, first proposed by John Wheeler and later realized in laboratories, suggests that reality may not be decided until long after an event has occurred. In these experiments, photons seem to retroactively determine whether they behaved as waves or particles, based on measurements performed in the future. To classical intuition, this borders on absurdity. To Everett's interpretation, however, there is no paradox. Every outcome exists, and the branching structure of reality accommodates both histories, woven seamlessly into the fabric of the multiverse. Entanglement adds yet another layer. When two particles interact, their states become correlated in a way that defies classical explanation. Measure the spin of one, and the spin of the other is instantly determined, no matter how far apart they are. Einstein, Podolsky, and Rosen called it spooky action at a distance. Decades later, experiments by Alain Aspect and many successors confirmed that entanglement is real, violating local hidden variables and supporting the strange predictions of quantum mechanics. In Everett's frame, entanglement is no mystery. Each outcome exists across branches, and correlations remain consistent within each universe. What seems like instantaneous coordination is simply the natural unfolding of branching worlds. From these experiments arose not only deeper confirmation of quantum mechanics, but new technologies. Quantum computing, still in its early decades, harnesses superposition itself. Unlike a classical bit, which is either 0 or 1, a quantum bit, a qubit, can be both 0 and 1 simultaneously until measured. By chaining many qubits together, a quantum computer can explore vast landscapes of possibilities in parallel. In Everett's picture, one might say that a quantum computer performs calculations across many worlds at once, with the final answer being the convergence of those branching computations. It is not proof of many worlds, but it reveals the uncanny power of quantum principles when used directly, rather than hidden behind classical outcomes. Yet even with these experimental wonders, the central riddle persists. If all outcomes exist, why do we perceive only one? This is the problem decoherence seeks to explain. Introduced in the late 20th century by theorists such as H. Dieter Z. and Wojciech Zurek, decoherence describes how fragile quantum states, when entangled with their environment, quickly lose their coherence. The delicate superpositions spread into countless degrees of freedom, photons, air molecules, thermal vibrations, until interference is no longer visible. To the observer, it appears as though the wave function has collapsed. In reality, the branches have merely separated, each becoming inaccessible to the others. Decoherence does not destroy superpositions. It hides them within the vast complexity of the environment. In this way, it grants Everett's vision a profound plausibility. The worlds split, but their isolation makes them seem as though only one remains. Still, the search for evidence presses on. Can many worlds ever leave a signature observable from within a single branch? Some physicists argue no, that the interpretation is empirically indistinguishable from Copenhagen or other frameworks. Others suggest subtle interference effects might one day reveal branching structure. Though no consensus exists, quantum experiments grow ever more refined, pushing coherence into larger systems. Molecules of hundreds of atoms have been placed into superposition, interfering with themselves. The larger the system, the stranger the implication. How large could a superposition be? Could an entire cat, or even a conscious brain, persist in such a state, awaiting branching? Then comes the deepest challenge: probability. In Everett's world, all outcomes happen. If so, why do observers perceive probabilities at all? Why does a coin still feel like a 50-50 chance, when in reality both heads and tails occur? This is the puzzle of the Born rule, the mathematical rule that gives probabilities in quantum mechanics. Everett attempted to derive the Born rule from the structure of branching universes, arguing that the measure of branches corresponds to probabilities as we experience them. Later theorists, such as David Deutsch and others, extended these arguments with decision theory, proposing that rational agents within many worlds should expect outcomes according to the Born rule, even though all outcomes occur. It remains a subtle and contentious issue, a reminder that Everett's vision, for all its elegance, still struggles with the language of chance. In this deeper investigation, the strangeness of quantum mechanics is not diminished, it is magnified. Experiments confirm again and again that the quantum world defies classical expectation. Decoherence explains why we perceive singular outcomes, but it does not erase the branching hidden beneath. Probability emerges as a measure of experience, but the mathematics insists on multiplicity. If Everett is correct, then every photon's path, every electron's spin, every radioactive decay, each one is not a coin flipped once, but a universe split in two. And in every branching, countless versions of reality diverge, each unaware of the others, each as real as the world we call our own. The further the investigation reached, the more unsettling its implications became. Everett's hypothesis, at first a daring attempt to remove ambiguity from quantum theory, began to cast shadows across every aspect of existence. What had started as mathematics now pressed against the walls of human identity, morality, and cosmology itself. The first and most intimate shock was philosophical. If reality branches with every quantum event, then the self is no longer unique. Each choice is not a singular step forward, but a fracture. At the moment of decision, versions of oneself separate, walking parallel corridors of fate. One speaks a word, another remains silent. One survives, another perishes. To imagine this is to confront a terrifying humility. The I that feels central and irreplaceable may be only one thread in a tapestry woven from countless versions of the same life. Consciousness feels whole, but in a many-worlds universe, it is endlessly repeated. The uniqueness of the self dissolves into a cosmic chorus of duplicates. The cosmological implications spiral even further. If branching is real, then the number of universes is not large, it is infinite. Every electron's spin, every photon's path, every fluctuation of a quantum field creates new realities. Infinity is not a distant abstraction, but the very fabric of existence, blooming with unstoppable proliferation. Our observable cosmos, vast and ancient though it is, becomes only one page in a book of endless length, each page written in parallel, each complete in itself. This raises questions that cut into morality. If every possible choice is taken somewhere, then what does responsibility mean? In one world, a hand saves, in another, it harms. Does this absolve or condemn? If all possibilities are realized, then morality itself risks dilution. Each action is both committed and avoided. Each virtue, mirrored by its opposite. The comfort of singular accountability unravels into a web of infinite duplications. Philosophers have wrestled with this. Does the existence of all possibilities erase the meaning of any one? Or does the path we perceive still carry the full weight of choice, even if shadow versions walk elsewhere? Meanwhile, cosmology began to encounter its own branching. The theory of inflation, proposed by Alan Guth and others, suggested that in the earliest instance after the Big Bang, the universe expanded faster than light, smoothing irregularities and seeding galaxies. Yet inflation does not end everywhere at once. In many models, it continues eternally, bubbling new universes into existence from quantum fluctuations in the vacuum. Each bubble becomes a universe with its own laws, its own history, its own unfolding. This inflationary multiverse bears striking resonance with Everett's vision, a cosmos of universes, constantly budding from the quantum foam. The difference is scale. Everett's branching occurs with every particle. Inflation's branching occurs with entire cosmic domains. Together, they suggest multiplicity, not as an exception, but as the rule. Even black holes, the darkest regions of space, may play their role. Some theories propose that when a singularity forms, it may give birth to a new universe beyond its horizon, shielded from ours by the very fabric of space-time. In this view, every collapse could be a genesis, every death of a star a branching into a hidden cosmos. Our universe itself may have been born from such a collapse, in a parent universe, one branch among many in a chain without end. With each branching, whether from quantum events, inflationary bubbles, or black hole births, Complexity increases without bound. Entropy, already the arrow of time, becomes intertwined with branching itself. Each split multiplies states, weaving more threads into the cosmic fabric. The multiverse, if real, is not only infinite, but ever diverging, a fractal that cannot be contained or reduced. And then comes the deeper mystery, one that haunts even the boldest minds. Does the multiverse undermine the very meaning of reality? If every possibility is real, then what does real mean? Is reality the sum of all branches, or only the one we perceive? Is consciousness the narrowing of infinite outcomes into a single narrative? Or is it an illusion of focus while endless versions of ourselves live on, unobserved? The escalation of the mystery leaves no certainty intact. The self is fractured, morality is clouded, cosmology is multiplied, entropy spreads into infinities, and reality itself trembles under the weight of too many versions. What began as a mathematical solution to the quantum puzzle has expanded into a question that threatens to dissolve the very definition of existence. In the silence of this mystery, one haunting possibility remains. Perhaps the universe is not one but many, and we are forever trapped within the blindness of a single thread, never to glimpse the others, yet always shadowed by their presence. The strangeness of quantum mechanics did not end with Everett's proposal. If anything, it widened the field of possibility, drawing rival interpretations and speculative models into an ongoing debate about the very fabric of reality. None can claim final proof. Each is a lens, a way of looking into the fog of the quantum world, and each reveals something both elegant and unsettling. The many worlds interpretation, Everett's daring vision, holds that every quantum outcome is realized. When an electron spin is measured, when a photon passes through a slit, the universe does not collapse into one outcome, it branches. In this endless proliferation, all possibilities exist, each contained in its own version of reality. No collapse, no privileged observer, only a cosmos of infinite branching worlds, seamless and eternal. The theory is mathematically consistent, requiring no alteration of quantum laws, yet it multiplies existence beyond comprehension, demanding an acceptance of infinity as the very essence of being. Against this stands the Copenhagen interpretation, first articulated by Niels Bohr and his colleagues. In this view, the wave function is a tool of knowledge, not a description of reality. Probabilities collapse into definite outcomes at the moment of measurement. Until then, particles exist as possibilities, not certainties. The Copenhagen approach is pragmatic, matching experiment with remarkable precision, yet it leaves unanswered the haunting question: what constitutes a measurement? Why should observation hold such cosmic power? For decades, this interpretation was the orthodoxy, but its philosophical vagueness has drawn unease from generations of physicists. Another alternative arose in the pilot wave theory, or Bohmian mechanics, proposed by Louis de Broglie and later refined by David Bohm. This interpretation seeks to restore determinism. Particles, in this vision, always have definite positions, guided by a pilot wave that informs their motion. There is no branching, no collapse, only hidden variables weaving beneath the surface. The cost is non-locality. The pilot wave must influence particles across distance instantaneously, a feature Einstein would have found deeply troubling. Yet the theory remains consistent with quantum predictions, offering a vision of order beneath apparent randomness. As experiments grew more precise, the concept of decoherence emerged as a bridge. Decoherence does not claim to solve the measurement problem, but it shows how quantum probabilities, when entangled with their environment, lose their ability to interfere. A particle superposed in multiple states spreads its coherence into air molecules, photons, vibrations. From the perspective of an observer, this looks like collapse. The worlds, in Everett's view, have split and now evolve separately, though they never again interact. Decoherence gives many worlds a mechanism for the apparent singularity we perceive, though it stops short of proving its existence. Beyond quantum mechanics itself lies cosmology. The theory of cosmic inflation suggests that the early universe underwent exponential expansion, smoothing its structure and seeding galaxies. Yet in many models, inflation is eternal, constantly spawning new bubble universes from quantum fluctuations. Each bubble expands, becomes a cosmos in its own right, and perhaps follows different physical laws. This inflationary multiverse resonates with Everett's branching. In both cases, multiplicity is not exception, but inevitability. Our observable universe may be one bubble among countless others, hidden beyond horizons we cannot cross. String theory adds yet another dimension. Literally, in its vast landscape of solutions, string theory permits on the order of trillion possible universes, each with its own physical constants, dimensions, and laws. This string theory landscape has been invoked to explain the fine-tuning of our universe, why the constants of nature permit stars, planets, and life. If there are vast numbers of universes, then some will, by chance, allow the conditions we see. To many, this feels unsatisfying. A multiverse of staggering scale, invoked to explain the peculiarities of one. Yet it remains a powerful vision of possibility, rooted in the mathematics of unification. Another development, quantum Darwinism, seeks to explain why certain outcomes rise to prominence. In this framework, the environment itself selects stable states, which proliferate and become the reality observers perceive. Just as biological evolution preserves traits that endure, quantum states that can be redundantly recorded across the environment dominate experience. This picture gives weight to why we perceive one thread of reality rather than another, though it remains an interpretation layered atop decoherence. Through these models runs a speculative thought that touches philosophy as much as physics. Perhaps consciousness itself experiences only one thread of reality. If countless branches exist, each containing versions of ourselves, then awareness may be the narrowing of infinite possibility into a singular flow. The other branches are no less real, but they are inaccessible, unseen, unremembered. Consciousness does not collapse the wave function, but it does create the illusion of unity, a self walking one path through a forest of infinite trails. Taken together, these theories and speculations weave a tapestry of profound complexity. Many worlds, Copenhagen, pilot waves, decoherence, inflationary multiverses, the string landscape, quantum Darwinism. Each offers a vision, each struggles with questions unanswered. None resolves the mystery entirely. All reveal that reality may be stranger than even imagination dares to hold. In the silence between theories, the question lingers: if all outcomes exist, if universes bloom from inflation, if string theory scatters reality into unfathomable landscapes, then what does it mean to live a single life on a single thread, aware only of this fragile moment? For all its elegance, the many worlds interpretation remains a vision suspended between mathematics and metaphysics. Its equations align with quantum mechanics. Its logic is uncompromising, but science demands more than coherence. It seeks evidence, traces of truth imprinted in the fabric of reality. To bridge the gap between speculation and verification, physicists have turned to their most powerful instruments, probing deeper into the quantum realm, stretching their gaze across the cosmos, and listening to the vibrations of space-time itself. For all its elegance, the many worlds interpretation remains a vision suspended between mathematics and metaphysics. Its equations align with quantum mechanics. Its logic is uncompromising, but science demands more than coherence. It seeks evidence, traces of truth imprinted in the fabric of reality. To bridge the gap between speculation and verification, physicists have turned to their most powerful instruments, probing deeper into the quantum realm, stretching their gaze across the cosmos, and listening to the vibrations of space-time itself. The frontiers begin beneath the Earth, in caverns of concrete and magnets, where particle accelerators hurl protons to near-light speed. At the Large Hadron Collider near Geneva, beams collide with energies that recreate conditions of the early universe. Detectors register showers of particles, revealing the substructure of quantum fields. Here, physicists search for cracks in the standard model, hidden variables, exotic particles, or asymmetries that might hint at physics beyond the known. While accelerators cannot peer directly into parallel worlds, they probe the rules that govern quantum behavior, rules upon which Everett's multiverse is founded. If new particles or fields were discovered, they could reshape the debate on whether branching realities are necessity or illusion. above the accelerator halls. In laboratories of mirrors and lasers, quantum optics experiments continue to push the boundary between the visible and the impossible. Entanglement has been confirmed over distances of hundreds of kilometers. Photons linked as if space itself were irrelevant. Quantum teleportation has transferred states of particles across space without moving matter, a triumph of correlation. Delayed choice experiments blur the line between past and future, suggesting that reality itself is unsettled until measured. Each of these experiments strengthens quantum theory's predictions, and each can be seen as compatible with Everett's branching. The universes multiply invisibly, leaving us only the patterns of interference and correlation as their shadows. Meanwhile, the rise of quantum computers offers a tangible encounter with parallelism. A classical machine processes information line by line, each step a singular calculation. A quantum computer, by contrast, places qubits into superposition, exploring multiple possibilities simultaneously. When the computation ends, the result appears as one outcome, but the calculation itself is enriched by the multiplicity beneath. To some, this is metaphor only. To others, it is a demonstration of many worlds in practice. The machine sampling countless branches of reality before collapsing into one thread. The debate is unsettled, but the machines work. Their existence is itself proof of quantum mechanics' uncanny truth. Beyond the laboratory, the cosmos itself becomes a stage for testing the multiverse. The cosmic microwave background, a faint afterglow of the Big Bang, stretches across the sky as a fossilized light from nearly 14 billion years ago. Within its patterns, scientists search for subtle anomalies, circular imprints, irregularities that could signal collisions between our universe and others, though no definitive signature has yet been found. The search continues, for if universes have brushed against one another, their scars may still be written in the heavens. Even space-time itself has become an instrument. The Laser Interferometer, Gravitational Wave Observatory, LIGO, listens for ripples in space-time caused by merging black holes and neutron stars. Some have wondered, could other universes, if they exist, leave subtle imprints upon this cosmic fabric? For now, the signals observed have matched Einstein's predictions precisely, but with each detection, instruments grow sharper, preparing for the possibility of anomalies that might whisper of realities beyond. Looking ahead, physicists propose even bolder tests. Macroscopic quantum interference experiments seek to place larger and larger systems into superposition, not just electrons or photons, but molecules, clusters, perhaps even microscopic life. If such superpositions endure before decoherence pulls them apart, it could confirm that quantum rules apply at scales once thought impossible. If many worlds is true, these experiments do not create new strangeness. They reveal what was always there, the silent branching of reality, even in systems we consider ordinary. Yet amid the ingenuity of these tools, a sobering debate remains. Can the many worlds interpretation ever be tested directly, or is it destined to remain interpretative? A framework as unfalsifiable as it is compelling. For every photon interferometer, for every entangled particle, for every cosmic survey, Copenhagen and Everett remain equally consistent with experiment. The equations do not favor one over the other. What changes is how we choose to read them. And so, science continues its vigil. Particle accelerators probe the depths of matter. Quantum optics stretches coherence into the macroscopic. Quantum computers harness superpositions for power. Telescopes search ancient light for cosmic signatures. Gravitational detectors listen to the tremors of space-time. Each experiment sharpens the paradox. Each confirms quantum mechanics, while leaving the interpretation unresolved. Perhaps the truth of many worlds will never be captured by an instrument. Perhaps the multiverse is not something to be proven, but something to be accepted or rejected as the most uncompromising reading of quantum law. Yet science does not rest. With every beam split, every wave detected, every signal gathered from the sky, humanity edges closer to an answer, even if that answer remains shrouded in infinities. In the silence of the laboratory and the vastness of the cosmos, the tools remain poised. They wait, not only to measure what is, but to reveal whether what is singular, or endlessly multiplied. Imagine an endless library, its shelves stretching beyond horizons the eye can never reach. Upon each rests a book, and within each book is a life, familiar yet different. One volume contains the story you know, the places you have walked, the faces you have loved, the choices you have made. But surrounding it are countless others, books that tell of paths you did not take, words you did not speak, lives you did not live. This library is the multiverse. Its silence is infinite, its shelves eternal. Every moment adds another volume, and the collection grows without end. If Everett is right, then every decision creates another version of us. Every hesitation, every heartbeat, every gesture fractures into possibilities, and none of them are lost. The life you did not live is not erased. It endures, written into the geometry of another world. Joys that slip through your fingers, sorrows that never touched you. They exist elsewhere, carried by other selves who share your name, your face, your origin. Yet within this strange comfort lies a haunting truth. Each of us is confined to our own thread. We cannot open the other books. We cannot meet the selves who turn differently at the crossroads. The library surrounds us, but its volumes are locked. Consciousness is the narrowing of infinity into a single story, read line by line. This reframes the question of free will. Do we carve our own path, or are all paths already written? In one sense, every possibility is realized, and choice is only the discovery of which thread we will follow. But in another, the act of choosing still matters, for it is through choice that we become aware of the story we inhabit. The dignity of life may not lie in altering the cosmos, but in experiencing, fully, the page we are given to read. For humanity, this vision is profound. Our lives are not unique because they are solitary, but because consciousness allows us only one journey among the countless that exist. This limitation is also our gift, the chance to feel the weight of each moment, to embrace its irreversibility, to live as though each step is singular, even while the multiverse blooms unseen around us. And so we arrive at a closing thought, as haunting as it is illuminating. If reality splits with every choice we make, then eternity is not in the stars above us, but in the infinite versions of ourselves we will never meet.